Hi everyone, welcome to another lecture in ChemE 122, and this time we are now going to be discussing power production using gas power cycles. Okay, so now for gas power cycles, this discussion revolves around the use of what we call reciprocating engines. Okay, so reciprocating engines are single devices, which are able to do a lot of work, in a small amount of volume. So for example, take this piston cylinder device, and this piston can actually function as an engine similar to the internal combustion engines that you find in your automobiles. So what does this piston do? We define what we call a stroke, okay? And the stroke of a piston is between two fixed positions known as your top dead center, TDC, and your bottom dead center, BDC. Okay, so your piston will now move between these two fixed positions, okay, thus doing work in the overall process. So now for pistons, we define what we call at the bottom dead center where the piston is at its maximum volume. This is known as your displacement volume. And at the top dead center, this is the smallest possible volume, and this is known as your clearance volume. Okay, so the maximum possible volume of your process is located at the BDC, and the smallest amount of volume in your process is located at the TDC. So from here, we can define what we call the compression ratio for any reciprocating engine R to be the ratio of the maximum to minimum volume in any gas cycle for any particular piston. And there are two general ways or modes of operation for heat addition in most internal combustion engines that we know of. Okay, one is known as your spark ignition engines, and the other are known as your compression ignition engines. Okay, so for spark ignition engines, the most common spark ignition engine are your gas-powered cycles, okay, gasoline or petrol, okay, if you're British. Okay, so this your actual four-stroke internal combustion engine is composed of four steps. Okay, so first you have nasa loob ng piston natin, you have your air-fuel mixture, which you will now compress. Okay, ko-compress natin yan to a certain position. So this is known as your compression stroke. Okay, and then after some time, once it reach this point in your cycle, you now have an ignition. And then at once the ignition happens, instantaneously tataas yung pressure for a fixed amount of volume. Okay, and then due to the high pressure buildup, the piston will now move down, and this is known as your power stroke. And then once the piston moves down, yun nga, it will do work, kaya siya tinatawag na power stroke. Okay, so next up, you now have your combustion products here that you need to expel. So the piston will now again move up so that you can now expel your exhaust gases, and this is known as your exhaust stroke. And lastly, the piston will now move down, okay? And with the movement of the piston, we'll now draw in an air-fuel mixture, which will now prepare our cycle to begin again. Okay, so this is the PV diagram for this actual four-stroke internal combustion engine. And as you can see from here, if you can simplify the process such that your process is composed of the reciprocation of your piston between two fixed steps only, or two fixed volumes only, the maximum volume and the minimum volume. Okay, so those four-stroke internal combustion engines are typically found in your larger engines, so yung mga nasa automobiles natin. Okay. However, you also have smaller internal combustion engines that are spark ignited, and these are known as your two-stroke engines. And for two-stroke engines, the intake and exhaust strokes are combined together with the compression and the power strokes. So with this, meron tayong mas simpleng heat engine or simpleng piston, okay, that can now expel and intake gases. Okay, and with this, they are slightly more compact. Ito yung mas ginagamit, okay, for simple devices that require motors, yung mga lawn mowers natin for grass cutting and things like that. So with this, the downside of these two-stroke engines is that they don't have a sufficient combustion. Kasi, di ba, your exhaust stroke and your intake stroke are combined together with the compression and power strokes. So with this, you might have some expelling, okay? When nag-exhaust ka, when you do your exhaust stroke here together with your compression stroke, you might expel some of your fuel-air mixture. Kaya minsan, pag yung mga lawn mowers, medyo may mga ngamoy kayo na gasolina. Okay, so yun yung one of the reasons for this, due to the inefficiencies of combustion of these two-stroke engines. Okay, so now for your ideal four-stroke spark ignition engine, we can model this as what you call your ideal Otto cycle. And your ideal Otto cycle, okay, now operates similarly, but instead we don't have the intake or the exhaust stroke, okay, since we assume that we only have a single working fluid to approximate the overall process. So from here, we start off with an isentropic compression, okay, to the TDC. Okay, so this is a work requiring step from state 1 to state 2, meron tayong isentropic compression, okay, from the highest volume to the largest volume. Okay, and at this step, once it reaches state 2, you now have heat addition. So dito mag-approximate yung pag-spark plug natin, yung pag-ignite ng air-fuel mixture to state 3, and then that heat addition step occurs instantaneously at this fixed volume, kaya tataas bigla yung pressure from state 2 to state 3. After that, okay, after now pag-increase ng pressure, you now have the isentropic expansion step, your work-producing step. Okay, the piston will now move down from state 3 to state 4. Okay, and this will now produce work isentropically. And lastly, we now need to reject heat at constant volume, okay, which is now state 4 to state 1. And then from here, we can now start the cycle all over again. Okay, so now let us try to obtain a function for the thermal efficiency of your cycle. So the thermal efficiency of any cycle is defined as the network, okay, divided by QH. Okay, technically dapat pala naka-absolute value yan kung gusto mong in terms of the proper notation. Okay, which is also equal to 1 minus the absolute value of QC over QH. Now, saan itong QC natin? This is the Q out, okay, and QH is Q in. So we can define QC is equal to CV delta T, okay, which is equal to CV times T1 minus T4 since we have a constant volume process, and QH is again a constant volume heat addition. Okay, so therefore QH is equal to CV times T3 minus T2. So therefore, thermal efficiency is equal to 1 minus T4 minus T1 all over T3 minus T2. Okay. However, we can also simplify this further through the following transformations. Okay, let us now try to develop a relationship between some of these temperatures, okay, through the relationship between the two volumes. Okay, recall that your Otto cycle now operates between two fixed volumes at your BDC and at your TDC. Okay, so V1 and V4, ito yung maximum possible volume, so equal sila. And the smallest volume is at the TDC where V2 is equal to V3. And we can now define what we call your compression ratio, which is R is equal to V1 over V2. Okay, so with this, let us try to develop more relationships between these two volumes and the temperatures of our cycle. And in order to do that, since na-consider natin yung heat addition and heat rejection steps, let's now consider the two isentropic compression and isentropic expansion steps. Okay, so start muna tayo dito sa isentropic compression step. Okay, so for isentropic compression step, so state 1 to 2, we have an adiabatic compression. Okay, so for adiabatic, therefore, you can define T2 V2 raised to gamma minus 1 is equal to T1 V1 raised to gamma minus 1. Okay, and we can also define this for the isentropic expansion step, where T4 V4 raised to gamma minus 1 is equal to T3 V3 raised to gamma minus 1. Then we can rearrange this. Okay, T4 over T3 is equal to V3 over V4, but V3 over V4, okay, is equal to V2 over V1. Okay, since these two are related, V3 over V4 is simply equal to 1 over R. Okay, therefore, this relationship is now equal to 1 over R raised to gamma minus 1. And similarly, for V1 and V2, you can define T1 over T2 is now equal to V2 over V1 raised to gamma minus 1, and this is equal to 1 over R raised to gamma minus 1. So as you can see now, the ratio V3 over V4 raised to gamma minus 1 is equal to V2 over V1 raised to gamma minus 1, and equals sila to 1 over R raised to gamma minus 1. Meaning, you can now have a relationship actually between T4, T3, T1, and T2. Okay, so using this for the thermal efficiency, okay, T4 over T3 is equal to 1 over R raised to gamma minus 1, and T1 over T2 is equal to 1 over R raised to gamma minus 1 as well. Meaning T4 over T3 is also equal to T1 over T2. Okay, so again, we have derived that thermal efficiency is equal to 1 minus T4 minus T1, okay, all over 1, T all over T3 minus T2. We can do now is we can factor out T1 sa numerator and factor out T2 sa denominator to obtain the following expression. Okay, so obtaining this following expression, meron tayong ratio na T4 over T1 and ratio na T3 over T2. And we have derived this relationship between these four temperatures, okay, from the adiabatic steps. And as you can see, we can rearrange this somehow such that si T1, lagyan natin dito, si T3, iangat natin. Okay? So you can get T4 over T1 is now equal to T3 over T2. So if T4 over T1 is equal to T3 over T2, these two should now be equal. Okay? So therefore, the thermal efficiency is now equal to 1 minus T1 over T2. Okay? So para siyang similar, di ba, sa Carnot cycle. Okay? However, you can also express T1 and T2 in terms of your compression ratio such that the thermal efficiency is also equal to 1 minus 1 over R raised to gamma minus 1. Since T1 over T2 is equal to 1 over R raised to gamma minus 1, which we have also previously derived. Okay, so with this, the thermal efficiency of the Otto engine is simply a function of the compression ratio. Okay? And with this, the higher the compression ratio, the higher the thermal efficiency of your cycle. Okay, so now consider this example. We have an ideal Otto cycle which has a compression ratio of 8, and we have air initially at 100 kPa and 290 Kelvin, which undergoes isentropic compression. And the magnitude of heat addition to the air was 23,200 kilojoules per kilomole. Assuming air behaves as an ideal gas, calculate the thermal efficiency of our cycle. Okay, so in order to calculate the thermal efficiency, again, we have already derived the relationship of the thermal efficiency of the Otto engine, okay, with the compression ratio. So thermal efficiency is equal to 1 minus 1 over R raised to gamma minus 1, where gamma is the heat capacity ratio, which is equal to 1.4 for air. So substituting the required values, you can now get a thermal efficiency of your Otto cycle to be 56.47%. Okay, so in order to fully know all the details of our cycle, just recall your ideal gas process calculations. So we won't be going over the process calculations for each step kasi nagawa na natin yan noong first part of this course, okay, for your energy balance for closed systems. So typically, your compression ratios for gasoline engines are around the range of 8 to 11 compression ratio. And actual spark ignition engines, okay, typically have thermal efficiencies that are roughly 50% of the ideal Otto engine operating within the same conditions. So na-calculate natin kanina na 56% na thermal efficiency, in actuality, nasa around 20 something, high 20 plus or high 30 plus percent yung thermal efficiency nun. Okay, so now, for spark ignition engines, we know that to increase the thermal efficiency, you must increase the compression ratio. Okay, so to increase the compression ratio, you want to further uh, decrease the volume of state 2 to somewhere around here, maybe. Okay. However, when you increase the compression ratio, you will also be increasing the working temperature of your cycle. Okay, so for example, ginawa niyo state 2 at this point, mas mataas yung temperature niyan compared sa temperature no original state natin. And with this, okay, as you increase the compression ratio, the working temperature will increase, and it is possible that even before the ignition step, your fuel-air mixture here, okay, will now auto-ignite due to the high temperature reached by your compression step. And this auto-ignition of your air-fuel mixture is known as your knocking. Okay, so with this, compression ratio can be increased if the auto-ignition point of the fuel is raised, okay, and this is referred to as our octane rating. So the higher the octane rating, okay, the less likely of knocking or auto-ignition of our fuel air mixture. Ayan. So with this, typically, your gasoline, okay, your auto-ignition temperature of gasoline, fuel, is much greater than or at least greater than the auto-ignition temperature of your diesel fuel. Kaya ginagamit for spark ignition engines ay gasoline. It's slightly dangerous to use diesel, okay? Kasi using diesel will lead to possible auto-ignition even before you reach the full compression step. Okay? So another type of ignition engines are known as your compression ignition engines. And the compression ignition engines operate similarly to spark ignition engines except for the compression and the fuel addition step. For your compression ignition engines, only air is compressed until, okay, the TDC, and once you reach the smallest volume, the fuel is now sprayed into the hot air mixture. So with this, unlike a spark ignition engine na literally spark mo yung air fuel mixture, okay, for a compression ignition engine, you will now spray your fuel into the hot air. Therefore, this fuel sprayed mixture will now auto-ignite with the hot air gases. Okay, so okay lang na mataas ang compression ratio for your diesel engines kasi yung kinocompress mo, uh, wala siyang fuel. Okay, you only spray the fuel once you reach the topmost part of your stroke in your piston. Okay, so ngayon, this is what the ideal diesel engine will look like in a PV diagram. And the only difference between the diesel engine and the auto engine is your heat addition step. Yung heat addition step sa auto engine natin occurs at constant volume. Okay, so ito si 3 kapag auto engine. Okay, but for a diesel engine, 3 is at this point. Okay, so auto engine, constant volume heat addition, but for the ideal diesel engine, the heat addition step occurs at approximately constant pressure. Okay, so with this, we now define what we call our cutoff ratio. The cutoff ratio is the ratio between V3 and V2. Kasi nangyayari sa diesel engine, once you now add your fuel to the compressed heated air, okay, the mixture will now auto-ignite, and spontaneously, what will happen is that won't occur at constant volume, okay, but rather due to the intense pressure buildup, or due to the intense, not pressure buildup, but rather the instantaneous combustion, okay, the piston will now immediately move down, okay, thus causing a displacement, okay, and this ratio of V3 to V2 is known as our cutoff ratio, okay, and if the cutoff ratio approaches 1, okay, V3 is equal to V2, you now approach your auto engine performance, okay, and then the step 3 to 4 and 4 to 1 are still the same processes. Okay, so with this, for the same compression ratio for a diesel and an auto engine, okay, the thermal efficiency of your diesel engine is less than your auto engine for the same compression ratio. Okay, however, your diesel engines typically operate at higher pressures or higher compression ratios since you can achieve much higher temperatures without the fear of auto ignition. And to derive the thermal efficiency of your diesel engine, you can make the similar calculations before. Okay? But now that performance of a diesel engine is dependent on two ratios. Okay? First, the compression ratio, and then, of course, your cutoff ratio. And as your cutoff ratio approaches 1, you now approximate an auto engine performance. And as I've mentioned earlier, the compression ratios for diesel engines are much higher compared to auto engines. Okay, so for auto engines between 8 to 11, okay, but for diesel engines between 12 to even as high as 23 in the compression ratio, since we don't have any fears, okay, of auto ignition. Now, the downside to diesel engines is that since we are relying on heating the air, okay, for instantaneous combustions, one problem for diesel engines, especially for colder climates, is that the ambient temperature of the air may be extremely cold, okay, such that even if you compress your air to much higher compression ratios, hindi pa siya aabot sa auto-ignition temperature ng inyong diesel or yung fuel. Okay, so with that, diesel engines also referred to as cold start. Okay, kasi pag malamig yung hangin, hindi magko-combust yung ating fuel. Hindi magko-combust yung fuel, hindi gagana yung engine natin. So typically, especially for colder climates, if you have diesel engines, you need to warm your air inside the piston initially first. Okay? But for warmer climates like the Philippines, it's not as much of a problem. Okay, so again, your diesel engines removes the complication of the auto ignition of your fuel-air mixture since you're now only compressing air. Okay? And with this, you can use cheaper or low-quality fuel. Kaya gumagamit tayo ng diesel, okay, which has lower auto-ignition than your um, gasoline. So typically, for the same compression ratios, your auto engines again will have higher efficiencies than diesel engines, okay, due to the cutoff ratio. However, as you also remove the complication of auto ignition, your diesel engines will now operate at much higher compression ratios, ranging from 12 to as high as 24. Therefore, typically diesel engines have higher thermal efficiencies since you're operating again at higher compression ratios. Okay, so again, let's consider this example for an ideal diesel cycle with air as the working fluid. Compression ratio is 18 with a cutoff ratio of 2. Okay, at the beginning of the compression process, your working fluid has the following conditions. With this, calculate the thermal efficiency of the cycle, assuming air is an ideal gas. Okay, so again, we're only calculating for the thermal efficiency. So in order to define all the states, again, you can just do all of the ideal gas process calculations. However, take note na baka hindi ganun kaganda assumption kasi ang taas nung compression ratio natin. Okay? But for now, let's assume na ideal gas. Sige. Okay, so assuming air is an ideal gas, the thermal efficiency is as a function of your compression ratio and your cutoff ratio. So just simply plug in the compression ratio of 18 and cutoff ratio of 2 and your heat capacity ratio, which is 1.4. So using this, you can now calculate the thermal efficiency of your diesel cycle to be now 63.16%. Okay, so you also have some other closed system cycles which are modified from your Carnot cycles. Okay, so one modification of the Carnot cycle is your Stirling cycle. In the Stirling cycle, instead of having two isentropic expansion and compression steps, you have isothermal expansion or compression steps. Okay, so pansin nyo, the Stirling cycle is slightly similar to your Otto engine, but this time, ano na siya, isothermal instead of isentropic expansion or compression. Okay, and you also have now your Ericsson cycle, which on a PV diagram, you have two isobaric steps and two isothermal steps. Okay, and last but not least, you also have open systems gas turbine engines. Okay, so you can also use combustion and use these combustion gases directly in a gas turbine to produce work instead of using steam as your working fluid. Okay, so your gas turbine engines are most commonly known as your Brayton cycle. Okay, so for your ideal Brayton cycle, you have two isentropic compression steps and two isobaric steps. Okay, one state 1 to 2 isentropic compression in a compressor. 2 to 3 you have constant pressure heat addition. 3 to 4 you have isentropic expansion in your turbine, which is the work producing step. Okay, and you also have constant pressure heat rejection, state 4 to state 1. Ayan. Okay, so now to derive the thermal efficiency of your Brayton cycle, we now define what we call your pressure ratio. And the pressure ratio is defined as the ratio of the two working pressures in our cycle, which is the higher pressure P2 or P3, since equal sila, and the lower pressure P1 is also equal to P4. Okay, so using energy balance calculations again, which is ginawa natin previously nung week 2, okay? And similarly to the derivation of your auto efficiency and your diesel efficiency, okay, you can now obtain the thermal efficiency of your Brayton cycle as follows, which is a function of the pressure ratio, okay, and of course your ideal gas heat capacity ratio. And as you can see from here, as you increase the pressure ratio of your ideal Brayton cycle, you will now increase your thermal efficiency. Okay? So typically, the pressure ratios of Brayton cycles operate on a larger range from pressure ratio of 5 to a pressure ratio of 20. Okay, so consider now the gas turbine power plant operating on an ideal Brayton cycle and has a pressure ratio of 8. So from here, we can now calculate the thermal efficiency of your Brayton cycle. It is a function of the pressure ratio. So simply plugging in the pressure ratio is 8 and the heat capacity ratio, which is 1.4, you can now get the thermal efficiency of this cycle to be 0.4480. Okay, to calculate the other states in the cycle, just proceed to your ideal gas process calculations once again. Okay, so with this ends our quick lecture on your gas-powered cycles, and the three most common ones that you will commonly find are your Otto, diesel, and Brayton cycles. Okay, and next topic naman natin will now be your introduction to refrigeration cycle. So baliktad na siya ng power production. So with this, thank you for listening and have a great day.